Our story begins not in a gleaming laboratory, but in the deep, dark past of our own species. Long before the written word, long before great cities rose from the dust, our ancestors were the world's first chemists. They did not have names for the processes they controlled, nor theories to explain them. They simply observed, they learned, and they transformed their world. It all started with a flicker of light and a burst of heat. Fire. This single discovery was perhaps the greatest chemical reaction ever harnessed by humankind. It provided warmth against the biting cold, a way to make food safer and more nutritious. This was chemistry in its purest, most intuitive form. From the embers of these ancient fires, another discovery emerged. Our ancestors found certain rocks, heavy and strange, that behaved differently in the heat. When these colorful stones were placed in the intense heat of a kiln, something magical happened. A gleaming liquid would seep out, cooling into a new, hard, and wonderfully useful material. This was the birth of metallurgy. Copper, bronze, iron, these metals changed everything. As civilizations grew, so too did our curiosity. The practical chemistry of the ancient world slowly gave way to a more mystical and ambitious pursuit. This was the age of alchemy. It flourished in the great intellectual centers of the world. The alchemists were part philosopher, part mystic, part proto-chemist. At the heart of their quest were two extraordinary goals. The first was the transmutation of base metals, like lead, into noble ones like gold. This required a legendary substance known as the Philosopher's Stone. This mythical catalyst was said to be the key, the one ingredient that could unlock the secrets of matter. The second great ambition was even more profound. They sought the secret to eternal life. This quest led them down countless strange paths. They distilled herbs, boiled minerals, studied the stars, believing that the cosmos and the human body were inextricably linked. Their laboratories were filled with strange glassware, bubbling concoctions, and cryptic texts. Though their ultimate goals were rooted in mysticism, the alchemists made invaluable contributions to our story. The world was changing. A new spirit of inquiry, of skepticism, of logic began to sweep across Europe. This was the Age of Enlightenment. Old ways based on mysticism and ancient authority were being challenged. They sought to understand the world not through secret symbols, but through careful observation. New pioneers began to measure. They used sensitive scales to weigh reactants and to weigh products afterward. Measurement was revolutionary. It brought precision and rigor that alchemy lacked. This quantitative approach unlocked laws governing matter. A new science needed a new language. Alchemist texts used poetic, confusing names, oil of vitriol, spirit of salt. A clear system of naming was required. This let scientists communicate across borders without ambiguity. If a chemist in Paris made a discovery, a chemist in London or Stockholm could replicate it. Focus shifted from the Philosopher's Stone to understanding the world's fundamental building blocks. In the late 18th century, one of the greatest mysteries puzzling the new chemists was the nature of fire. For centuries, it was believed that when something burned, it released a mysterious substance called phlogiston into the air. But there was a problem. When metals were burned in air, they became heavier, not lighter. The answer would come from a brilliant and meticulous French nobleman, Antoine Laurent Lavoisier. Lavoisier brought an obsessive precision to his work. In a series of groundbreaking experiments, he heated mercury in a sealed container with limited air. He watched as a reddish powder slowly formed. As it formed, the volume of air decreased by about 1/5. He then heated the red powder more strongly and saw something astonishing. It turned back into mercury and released a gas that had exactly the same volume as the air that had been used up in the first experiment. This was the moment of revelation. Lavoisier had discovered that air was not a single element. It was a mixture. He called it oxygen, from the Greek words for acid former. He initially believed it was the essential component of all acids. He demonstrated that burning was not the release of mythical phlogiston, but the rapid combination of a substance with oxygen. Lavoisier's work was a revolution. He established the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed, only rearranged. Tragically, Lavoisier's life was cut short by the French Revolution. His legacy is immense. He is often called the father of modern chemistry. By the middle of the 19th century, chemists had discovered dozens of elements. Each had its own unique properties. Some were reactive gases, others were shiny metals, some were heavy and some were light. But it was a chaotic collection of facts. There seemed to be no underlying pattern. It was like a library full of books scattered on the floor. Many scientists tried to find a pattern, but no one could unite them all. The breakthrough came from Dmitri Mendeleev. He wrote the properties of 63 elements on cards, one per card. He arranged them like solitaire, by properties, then by atomic weight. He shuffled and reshuffled the cards, searching for a pattern. Then, in a flash of insight and a dream, he saw the solution. Arrange by increasing atomic weight, start a new row when properties repeat. This formed a grid, the periodic table. Elements with similar behavior fell into the same columns: alkali metals, noble gases. It was elegant and ordered. His table was visionary because it predicted missing elements. He left gaps in his table, declaring these represented undiscovered elements. Based on their position, he predicted the properties of missing elements with astonishing accuracy. He described their atomic weight, their density, and what compounds they would form. Within years, chemists discovered gallium, scandium, and germanium, and their properties matched Mendeleev's predictions almost perfectly. The world of chemistry was stunned. The periodic table was not just a clever arrangement, it was a deep truth about the nature of matter. For centuries, the idea of the atom, a fundamental, indivisible particle of matter, was just a philosophical concept. It was a useful idea, but there was no proof. First proposed by the ancient Greeks, Lavoisier, Mendeleev, they had worked with elements as fundamental particles but could not see them. The atom remained in theory. However, as the 19th century drew to a close, a series of astonishing discoveries would finally pull back the curtain. The first clue came from experiments with electricity. Scientists were passing high-voltage currents through glass tubes from which most air had been removed. They noticed a mysterious glow. A beam of rays streamed from the negative electrode, the cathode. In 1897, English physicist J.J. Thomson conducted ingenious experiments on these cathode rays. He showed the rays could be bent by electric and magnetic fields. This meant they were tiny, negatively charged particles. He had discovered the first subatomic particle, the electron. This discovery was earth-shattering. It meant the atom was not indivisible. Thomson proposed the plum pudding model. The next discovery came from Thomson's former student, Ernest Rutherford. His famous gold foil experiment was a masterpiece of scientific inquiry. He fired alpha particles at incredibly thin gold foil. According to the plum pudding model, these should have passed straight through with minor deflections, and most did. But to his astonishment, a tiny fraction, about 1 in 8,000, bounced almost straight back. This could only mean the positive charge was not spread out like pudding, but concentrated in a tiny, incredibly dense core, the nucleus. The atom was mostly empty space. Just as the atom was revealing its structure, another mysterious phenomenon was discovered, completely by accident. In 1896, French physicist Henri Becquerel was studying minerals that glowed after sun exposure, investigating whether they emitted newly discovered X-rays. One cloudy day, he stored uranium salt in a drawer on a wrapped photographic plate. Days later, he found a strong crystal image, as if exposed to bright light. This discovery captivated brilliant Polish scientist Maria Skłodowska, known as Marie Curie. She made this phenomenon her doctoral thesis subject. Working with husband Pierre Curie, she systematically searched for other radioactive substances. She coined the term radioactivity. Marie's work was incredibly arduous. Using instruments to measure faint electrical currents, she found pitch-blende ore far more radioactive than its uranium content explained. She reasoned it contained tiny amounts of more powerful radioactive elements. In a drafty shed, they began separating tons of pitch-blende ore. It was grueling physical labor, stirring huge vats of caustic chemicals. After years of effort, they succeeded in isolating not one, but 2 new radioactive elements. The first she named polonium, honoring occupied Poland. The second, glowing faint blue in darkness, she named radium. For these discoveries, Marie Curie became the first woman to win a Nobel Prize, and later, the only person to win Nobel Prizes in 2 different scientific fields. Her work opened a completely new field of science, showing that atoms were not stable and unchanging, but could spontaneously decay. They could transform into other elements and release enormous amounts of energy in the process. The fundamental discoveries of the past have unleashed a torrent of innovation that has completely reshaped our modern world. Today's chemists are the new alchemists, but instead of trying to turn lead into gold, they transform simple raw materials like oil, air, and minerals into the vast array of substances that underpin our civilization. Consider the field of medicine. The development of new drugs is a triumph of modern chemistry. Scientists can design molecules with incredible precision, creating antibiotics, painkillers, complex therapies for cancer and HIV. The sterile plastics, anesthetics, and diagnostic tests are all products of the chemical laboratory, saving countless lives globally. Look around you. The screen you're looking at, the chair you're sitting on, the paint on the walls, all are gifts of chemistry. Chemists have created polymers of astounding versatility. These can be incredibly strong yet lightweight, as in aircraft composites, or soft and flexible for food packaging. We're no longer limited to wood, stone, and metal. We can design materials with any property we desire. Chemistry is at the heart of feeding our growing population. The synthesis of fertilizers, starting with the Haber-Bosch process, has been called the most important invention of the 20th century. It has dramatically increased crop yields to sustain billions. Chemists also develop safe pesticides to protect crops, and work to ensure the safety and nutritional quality of our food supply. From the grandest structures to the most intimate health details, the hand of the chemist is everywhere. As we stand in the 21st century, the journey of chemistry is far from over. The challenges and opportunities have never been greater. The very successes of the past have created new problems that only chemistry can help solve. We face a warming planet due to carbon dioxide from fossil fuels. We face dwindling natural resources and the challenge of managing waste from our material-rich societies. The chemists of today and tomorrow are on the front lines searching for solutions. The future of chemistry is green. Green chemistry seeks to design products and processes inherently safer for human health and the environment. This means creating biodegradable plastics, developing processes using less energy, finding renewable feedstocks to replace fossil fuels. Chemists are using sunlight to split water into hydrogen fuel, designing catalysts that turn waste into valuable materials. At the other extreme, chemistry is diving into the infinitesimally small. Nanotechnology allows us to build materials and machines on the scale of individual atoms and molecules. Imagine nanobots destroying cancer cells without harming healthy tissue, or materials that repair themselves like living skin. Chemists are manipulating matter with control, once considered science fiction, opening possibilities for new medicines, ultra-efficient electronics, incredibly strong materials. Our quest for knowledge continues. We're still uncovering how molecules interact, how life emerged from chemical soup, what new properties matter can have under extreme conditions. Chemistry remains the central science, bridging fundamental particle physics to complex living biology. From the first spark in an ancient cave to the gleaming laboratories of the future, the story of chemistry is the story of human curiosity. The next great discovery is out there, waiting in a flask, a computer model, or the mind of a curious chemist. The adventure has only just begun.